All right, you're on.
Okay, it's my pleasure to start the last session of this exciting workshop. And the first speaker is going to be Yiyang Zheng, and he is going to talk about novel quantum Hall effects in multi-layer graphene.
Thanks for the introduction, Aaron. So I'm Yihan Zhen from Columbia University. I actually just graduated and moved to Cornell, but today I'll talk about my work done at Columbia with Corey Dean. So it seems like my internet connection is not that stable, so I'm turning off my video feed just to make this go a bit smooth. Yeah, so today my talk will be about our new findings on the nu equals to 1 state in a graphene double layer system in the quantum Hall regime. And by tuning a few experimental knobs, such as the magnetic field layer density imbalance, we can construct a 2-dimensional phase diagram of such state. So as is probably well known in the audience, that in a double layer quantum well system, when each layer is at the half-filled Landau level, if the Coulomb interaction between the two layers is strong enough, it is energetically unfavorable to occupy the same orbit in the XY plane in both layers. And it turns out if you view the empty size in one layer as holes with positive charge, or basically do a particle-hole transformation in one layer, the empty size or positive charge just rests right on top of the electrons from the opposite layer, and they kind of form effectively an indirect excitons, which have a long lifetime and can condense into a Bose condensate at low temperature. And experiments in gallium arsenide double well and graphene double layers have demonstrated dissipationless transport in counterflow measurement as a consequence of the condensate of indirect excitons. And the quantum Hall double layer system we study here features the two sheets of monolayer graphene separated by a thin few nanometer HBN tunnel barrier. And in this sample, we incorporate the graphite top gate top gate electrode and bottom gate electrode to independently control the carrier density in each graphene layer. And in this work, we primarily use the Coulomb drag measurement to probe the layer correlation, which in the Hall bar geometry, we drive current in only one layer and measure the voltage drop in both layers. And in the exciton condensate phase at nu total filling equal to -1. So in graphene, it is electron hole symmetric. So nu equal to -1 is the same as nu equal to 1. So in the exciton condensate phase here, the longitudinal resistance vanishes, and as a result of the dissipationless transport and the Hall resistance in both layers are quantized to 1 resistance quantum. And similar Coulomb drag experiment can be done also in Corbino geometry, which directly couples to the excitonic bulk. So we again flow current only through from the outer electrode in one layer to the inner electrode to the same layer. But in this case, we measure the current flowing through the passive layer if we connect the outside and inside electrode of that passive layer. So what we are plotting here is the ratio between the passive current to the current we drive in the system. And in the exciton condensate phase, all the charge carrier or the charge current is carried by excitons, and this results in the equal amount of passive current in that layer, which is equivalent to the current ratio of 1 at nu equal to 1. So alternatively, there's if one applied the same direction of electric field in both layers, one can probe the charge transport, and evidently in an system that is it has no unpaired electrons, it behaves just like an insulator at nu equal to 1. So the pairing strength in the system can be characterized by the by the ratio between the interlayered Coulomb interaction and the intralayer Coulomb interaction. And historically, people use the ratio D over LB to characterize the effective pairing strength. Here, D is the interlayer separation, and it is the same in the same device, and we can make it different with the different tunnel barrier thickness, and LB is just the magnetic length. At high magnetic field, D is smaller compared to the magnetic length, and that gives a weaker interlayer coupling. And in the quantum Hall binary system, as long as the total electron filling fraction equals to 1, after the particle Hall transformation, the two layers always end up having the same amount of electrons and holes. And it was also found in the epsilon condensate phase that the phase boundary got pushed even further to higher DYLB at when there is a finite non-zero layer imbalance, but the quantitative understanding of the role played by density imbalance is still unclear. In the rest of the talk, I will try to apply different measurement configuration while we continuously control these two parameters. So here I'm showing on the left is the longitudinal resistance, and on the right, the Hall resistance in the passive layer or the drag layer as a function of the layer imbalance as the x-axis, and y-axis the D over LB ratio. So the epsilon condensate phase exhibits zero longitudinal resistance and quantized Hall resistance in the drag layer, which corresponds to the light blue color on the left graph, and the coral color on the right. And we can see it appears mostly when the unbalance is not too large and the DOLB is not too high. And we also observe a series of lobes emerging at high DYLB. They correspond to the layer decoupled Jane states at 1/3 plus 2/3, 2/5 plus 3/5, and so on. So we also measure the Coulomb drag current ratio in the Corbino samples in the same parameter space, and it's qualitatively the same as the Hall resistance. This is expected because they both reflect the exciton ratio in the system. So now we'll first sit at layer balance case when both layers is half filled and study the response as a function of the DO-LB ratio. And the left figure shows the longitudinal resistance in red and the Hall resistance in the drag layer in blue as a function of DO-LB. So from left to right is strong layer coupling to weak layer coupling. And the signature of epsilon condensate, namely zero longitudinal resistance and quantized Hall resistance, persists up to slightly above 0.9 in DO-LB. And then the Hall resistance slowly decreases to 0 above DO-LB around 1.3, where the two layers seem to lose all layer correlation between them. And the ground state is supposedly two decoupled copies of composite Fermi surface. And we also see that in the middle of the transition, RX has a maximum. And this behavior is consistent with what people observed before in gallium arsenide double well. And also we noticed that the current drag ratio in Corbino shows very similar behavior and similar critical values as the Hall resistance, again, in Hall bar. And I want to point out that it's not well understood what's going on in the crossover regime, and even in the epsilon condensate phase, what is the correct picture to understand the pairing mechanism at finite D over LB. So here we are trying to provide some insights by looking at the temperature dependence. So as temperature increases, shown on the left, the Hall resistance in the passive layer starts dropping from unity. If you trace the red curve, it's around 1.8 Kelvin-ish, and we define that as the critical temperature, TC. And similar to what's proposed in this recent archive paper, we can define the pairing temperature of excitons at a small value of Hall resistance in a drag layer, for instance, at 30%. And we can then plot all the traces at different DOLB together into a 2D color plot and identify the contours of the critical temperature TC and pairing temperature as a function of DOLB. On the left is the longitudinal resistance, and on the right is the Hall resistance. And clearly, these two temperature shows distinct behavior against DOLB ratio, where TC shows a dome-like shape and T pair seems to be exponentially decreasing with DOLB. And above critical DOLB, we also realize an insulator-like behavior as shown in the middle panel measured in the parallel flow configuration in Corbino, where it probes the charge excitation. So I'm talking about the DOLB range between 0.9 and 1.3, basically the second dome here. And the layer correlated insulator disappears at 1.3 in DOLB when the two layers are decoupled, which is identified also by the Coulomb drag measurement. So both the insulator-like temperature dependence and the finite drag response suggest residual exciton coupling above critical DOLB of the condensate phase. And we named this phase the preform exciton phase here. And this is also consistent with Eisenstein's recent finding of the exciton condensate precursor above critical DOLB. And there is an intriguing dip in the charge gap at DOLB equal to 0.8, which marks also the onset of the high temperature preform exciton phase. So we can then just keep the two traces for the temperature TC and T pair as a function of DOLB and in the x-axis, and we now know we can basically write down what's actually in the ground state in different part of the phase diagram. So, and if BCS crossover phase diagram in the context of cold atoms, we see they show remarkable resemblance. And also the pseudo gap phase on the right here is a result of the preformed Cooper pairs in the BCS limit, but in our case, it's just preformed excitons. And we also noticed that a good indicator for this crossover would be the difference between the pairing temperature and the critical temperature, which we define as delta T here, T pair minus TC. And so far, we've been focused on what's happening as we tune DOLB ratio sitting at the balance case. And we can alternatively look at the temperature dependence at different density imbalance, but at the same DOLB or at the same magnetic field. So it is shown on the right. These two traces are taken at the same DOLB, but very different density imbalance. And these two shows very different temperature dependence. One is much smoother, and the other is sharper. And this is quite similar to the change at different DOLB. And it suggests that BEC to BCS like crossover as a function of layer density imbalance can be also achieved by tuning the density imbalance. And so as mentioned in previous slide, we can use the indicator delta T as the difference between the pairing temperature and critical temperature as an indicator to track the BCEC to BCS crossover as we tune the two knobs. And that's what I'm plotting here in the middle color plot. I'm plotting the delta T as in color, and black color means small delta T, which is more closer to the BCS end, and white color is more closer to the BEC. And the data points in different colors here correspond to the contour of constant delta t. And the shape of the contour gives us more quantitative information on how the layer density imbalance affects the pairing strength, or how the two parameters together affects the pairing strength. And we notice that this rounded V shape is actually defined or can be well fitted by the constant exciton density, which is equal to the filling fraction of the exciton times the magnetic field. And again, from the simple cartoon I put here, the filling fraction of excitons is approximately equal to that of the minority carrier in each layer for either electron or hole. For instance, if you have 1/3 in one layer and 2/3 in other layer, you particle hole transform the 2/3 layer, and you end up with 1/3 filling of excitons in the system. So basically, once you imbalance the layer, the exciton density just gets lower and is more going towards the BEC land. And one can just write down the exciton filling fraction as a function of the layer imbalance in this simple form. And if we replot the contour lines as a function of the average particle separation, which is just one, which is proportional to 1 over the square root of exciton density, we see all the contours become relatively almost independent of delta nu, which means that the pairing strength of the exciton superfluid is actually controlled by the ratio of D over L, where L is the average distance between the particles in the system. Okay, so far we've identified the evolution of pairing strength and the BEC to BCS like crossover in the exciton condensate phase in the two parameter space, and also the crossover between the condensate to the preformed exciton and eventually to a decoupled Fermi surface. And also we have a bunch of phase transitions to decoupled single layer fractional quantum Hall state at large D over LB. But what catch our eye is that the exciton transport becomes insulating. So on the right, I'm plotting essentially the counterflow conductance. It becomes insulating at a relatively high filling fraction compared to one would expect for the Landau level edge, which is delta nu equal to 1. So we wonder what's going on here at a large layer imbalance. So here we zoom into the large imbalance regime. On the left, I'm plotting the parallel flow conductance in Corbino as a function of total filling fraction and layer imbalance. So along total filling fraction nu equal to 1 is the excitonic state. Color here is insulating. And the middle panel shows the counterflow conductance also in Corbino, and which couples to the obviously the exciton transport. And it actually shows, the bright feature here corresponds to the to high counterflow conductance and corresponds to the exciton superfluid phase. And we see a sharp phase transition at approximately the imbalance equal to 0.5 filling from an exciton superfluid phase to an exciton insulating phase. And this suggests that the underlying, so combining these two information, even though, so this part, the excitonic order of this part is actually verified by the feature along the nu equal to 1 line in the parallel flow measurement. And we wonder if this could be a excitonic version of Wigner crystal, because we know that at small electron filling in a single layer system, electrons can form this spatially ordered Wigner crystal phase. So naturally, we want to increase temperature and see if we can actually melt the Wigner crystal. So the middle plot shows the current drag ratio in the Corvino geometry as a function of temperature. So when we park at the blue dot, the suspected or the candidate for the excitonic solid phase, the drag ratio, the current drag ratio reaches unity at an intermediate temperature range, suggesting the exciton superfluid ground state. At low temperature, both channels becomes insulating, both the excitonic transport and the electron transport becomes insulating. So you just see a fluctuating behavior because of measurement noise. It's probably more clear in the Hall bar measurement, Coulomb drag configuration as well. And the black curve here is the Hall resistance, and the red curve is longitudinal resistance. So at low temperature still, it fluctuates a lot because it's too insulating in a drive layer, no current can pass through. But in the intermediate temperature range, we see near zero longitudinal resistance and Hall resistance in a drag layer within 10% of unity. And this suggests that the ground state at intermediate, the state at intermediate temperature is an exciton superfluid phase. So we can further map out the finite temperature phase diagram versus the layer imbalance and temperature in the counterflow configuration. So the exciton superfluid pocket is identified by low resistance in blue color in this plot, and the integer quantum Hall state corresponded to the extremely insulating region in red. And we notice a sharp white curve emanating from the integer gap at high temperature and dropping towards a smaller imbalance at low temperature. And if we zoom in this white curve at low temperature, we actually observe a hysteretic behavior across the white curve, which we think corresponds to the formation of domains in the excitonic Wigner crystal phase. This can be obtained from the Hall bar to the Hall resistance in Hall bar measurement, where the red or unity Hall resistance marks the superfluid phase, and the low temperature pocket with diverging response corresponds to the exciton solid phase. And the boundary with between the integer quantum Hall state is identified by the hysteretic peak. And also, you can also kind of extrapolate the temperature dependence which evolved from the integer quantum Hall effect down to low temperature, and get the critical delta nu for the exciton solid phase. So from the finite temperature phase diagram, we realize the excitonic solid phase here is almost entirely the extruding superfluid dome in temperature. In other words, the melted exciton solid phase always has quasi-long range phase coherence at intermediate temperature. So it hints that from the point of view of energetics, that the quasi-long range phase coherence could persist down to the low temperature solid phase. So integrating all the information together, we're able to complete the low temperature phase diagram of the total filling fraction equal to 1 ground state in the double layer system. And we have pretty rich quantum phase. Remarkably, in this system, we obtained this phase diagram within a single device. Okay, so in the rest time of the talk, I would like to switch gears and talk briefly about our the new system we've been working on, which is a triple layer graphing system. Similar to a double layer system, we have 3 layers of monolayer graphene separated by 2 HBM tunnel barriers, and the carrier density in each monolayer graphene sheet can be independently tuned by both the top gate voltage, the back gate voltage, and the bias to one of the graphene layers. And the quantity we measure is the penetration capacitance, which is sensitive to which is inversely proportional to the charge compressibility of the 3 layers altogether. So here is an example plot. If we fix the bottom layer filling fraction at 1/2 and sweep against the top layer filling fraction and middle layer filling fraction, and the color here corresponds to the penetration capacitance between the 2 gates. And bright color means large penetration capacitance, which is incompressible of all 3 layers altogether. So we see that we don't actually see any 2-layer states along nu total equal to 1, but rather we see the 2 most insulating features are along the 3-layer total filling equal to 1, which is here, and the 3-layer total filling equal to 2 here. So to further demonstrate that this is actually a constant 3-layer total filling, we can step the filling fraction in the bottom layer while taking the same 2D scan. So this is we start at the bottom layer filling equal to 0.3, and now still the 2 most prominent features correspond to 3-layer total filling equal to 1 and 2. And as we increase the bottom layer filling, the 2 lines moves downwards towards a low filling fraction of the rest 2 layers while maintaining the 3-layer total filling. So with this measurement, we unambiguously show that the stage we're looking at is actually a 3-layer happens only at 3-layer when the total filling fraction of all 3 layers equals integer. So we can basically scan on the surface of the total filling of 3 layers in the 3D space, but this is just a 2D slice of the 3D space. So we can see that it's actually always gap everywhere on the nu total equal to 1 plane, although the charge gap does vary a bit as a function of the middle layer filling fraction. And we notice that for the nu equal to 1 state, it is more robust when charge populates the middle layer, and for the nu equals 2 state, it's more robust when charge populates the outer layer. And this actually agrees with theory and previous study in a wide quantum well in gallium arsenide system, because it actually, according to calculation, minimizes the overall energy. So to summarize this part, we observed integer quantum Hall effect in a triple layer graphene system. And most likely this just triple layer state is layer coherent because it happens at arbitrarily, it happens regardless of the charge distribution among all 3 layers as long as the total filling fraction is integer. And there are also hints for fractional fractional quantum Hall state in the triple layer system, which I'm not showing here. And so at last, I want to acknowledge my colleagues and collaborators at different institutions, and also the Mac lab, which we perform. And thank you for your attention. I'm ready to take questions.
Okay, thank you Thank you very much. And we have a few minutes for discussion. There's a question already on the chat. It's from Janandra Jain. And maybe Janandra, why don't you phrase your question by exactly?
Okay. Can you go back to your phase diagram as a function of delta nu and d over, yeah, the one that, this one. So I'm struck by the fact that this BEC superfluid phase extends in the flanks to fairly large values of d over LB. Do you have an understanding of that, or do you know how far it really goes?
Yeah, that's a good point. This really is, it seems like outside of 1/3, the pairing strength is pretty different from within 1/3. So I'm wondering if there has something to do with the commodity Fermi surface below and above 1/3. I mean, in terms of the competition between the momentum space pairing versus real space pairing. And experimentally, we only measure up to DOLB equal to 1.6, but seems like it's also pretty robust. It's still pretty robust up to 1.6.
I see. Thank you.
Yep.
Mansour?
Yes, I have a question. You mentioned near the end that the fractional quantum Hall that you see is stronger when you have these other layers. Do you have any comment? Why is it? Why is it because there's less disorder, or is there something more fundamental?
Fractional quantum Hall?
Yeah, and I think in one of your last slides, you said, without going into the details, you said.
It's not actually stronger. I actually meant we actually saw this evidence for 3-layer coherent fractional quantum Hall states.
Okay, I
But
misunderstood.
it's actually weaker than integer states. Yeah.
I misunderstood. Okay, thanks.
No problem.
Okay, I have a question. I don't remember Jim's data in detail, but it seems to be that overall, some of your striking effects, like the superfluid states, they exist in your samples at a higher temperature than those in gallium arsenide. Is that correct? I mean, you're talking about temperatures which are several degrees Kelvin.
Yeah, so the TC here is on the order of several Kelvin in graphene double layer structures. I mean, depending on the interlayer separation.
And you remember Jim's data? I mean, what is his temperature range is on the left panel that you're showing now. It's 0.3 Kelvin.
Oh no, so I think
no, I'm sorry.
Yeah.
So you remember Jim's the data that in gallium arsenide, what is the typical temperature range?
Yeah, I think maybe Mansour can answer the question better, but to my memory, it's like below Kelvin, definitely, right?
I mean, let me make a couple of comments. So, I mean, the temperatures are of the order of Kelvin, about 1 Kelvin. But this TC, I guess the way you're defining it here, which is resistance going flat and then coming down, becoming activated, that we actually saw back in 1997, many years ago, and in wide quantum wells. So that temperature was around 1 Kelvin, between 1.5 Kelvin to 0.5 Kelvin. And the amazing thing was, as you change the parameters of the system, mainly D over L in a way, you could see that this temperature changes, even though the gaps are exactly the same. The gaps were huge. The gaps were like 20 Kelvin or so, 10 Kelvin. But the onset of this resistance becoming activated strongly depended on that D over L. So we interpret it as a critical temperature, essentially a finite temperature, possibly a Koster-Thouless transition. So it has some similarities to this.
Well, thank you, Mansour. So we, at this point, we have no more questions. So maybe.
Oh, I'm sorry, there is a question by.
Oh, Barbert.
Klaus?
Yeah,
Yeah.
I'm sorry.
Yeah.
So there's a
Sorry.
question by Klaus. Klaus, can you unmute yourself and ask?
Yes, I just wanted to know what are the main differences if you replace one layer by real holes?
By real holes. So in graphing, actually, all the symmetry breaking state is the same. Basically, at along, let's say nu equal to 0, total filling of 2 layers nu equal to 0, meaning that one layer is in the electron side, one layer is the whole side, whole branch of the Landau level. It still, we basically see the same result. This is just a consequence of, graphene is electron hole symmetric, and it's a 4-fold degenerate Landau level. So between -2 and 2 is each Landau level is basically the same.
Bert, you have a comment on gallium arsenide and superfluid phase. Do you want to? You want me to repeat the comment, or would you like to unmute yourself and just?
Well, it's partly a comment, but it's just when people are trying to compare differences between what was seen as a function of temperature, for example, in gallium arsenide, and here it's well, perhaps the most striking difference is that it appears quite a difference in what the critical separation is even at low temperatures. The gallium arsenide seems to be able to go to quite a bit higher D over LB and still be in the superfluid phase for whatever reason than here. And what the differences are, I don't think they're very well understood. Obviously, there's screening differences. A lot of things are different, but I don't think it's quite understood why the transition is so small here. There's D over LB equals 1 is a pretty small value for that transition temperature, and I don't think transition separation.
Yeah,
Bert, maybe I could make a comment there. So it turns out the finite layer thickness is important. I know for a fact for 1/2 state, for the 1/4 plus 1/4 fractional quantum Hall state, theory and double quantum well data show D over L of the order of 2. But in wide quantum wells where they have very thick wave functions, we see it up to D over L of even 5 or 6. So my guess is that this is possibly related to that the gallium arsenide samples, the width of the quantum well, each is around 150 or 200 angstroms. So the wave function is not the delta function. And my guess is that's the difference.
Okay. Well, thank you, Mansoor. And I thank Yihan again for not only the excellent talk, but the excellent research, and my best wishes in your new job. So we proceed now to the next talk by.
Actually, could I just make just a final? There are differences. I think it's a little surprising to me that you lose the superconductivity there are differences, but I still think it's not understood why the value of D over LB is so small. The critical value. Sorry. Yep.
Okay. Thank you, Bert. So our next speaker is Professor Jun Zhu of Penn State University. Jun will talk about probing valley and spin degrees of freedom in bilayer graphene. Please go ahead, Jun.
Thanks very much, Aaron. I'm Jun Zhu. I'm from Penn State. I'd first like to thank the organizers, especially Mansoor, for putting together this wonderful workshop. There's been a lot of beautiful talks throughout the week. I wanted to focus on telling you about how we use the valley isospin in bilayer graphene to control ground states of fractional quantum Hall effect. So I'll start by telling you that the monolayer graphene, remember, it's a honeycomb lattice, and there are two inequivalent valleys, K and K prime. And because of the inversion symmetry between the two sublattices, it doesn't have a band gap. Now, when you take two monolayer graphenes and shift it, and then stack them on top of each other, you get Bernal stacked bilayer graphene. So there are two atoms that stack on top of each other. These form high energy bands. These B1 and A2, these two unstacked atoms form the low energy bands of bilayer graphene. Now it is a two-dig with quite small masses and considerable electron hole asymmetry, as you can see here. There's also a touching point in the band structure because of the inversion symmetry between the B1 and A2 site. Now we can break that by applying a vertical electric field through the bilayer using two gates. And that gives these two sites different electrostatic potentials. And that is the origin of the electric field induced band gap in bilayer graphene. So with the applied displacement field, we can go up to a few hundred millivolt in band gap. And as we become better and better in making cleaner and cleaner samples, we can look at the small gap regime better and better. And you can see that this linear relationship between delta and D persists all the way to very low displacement field. For every 1 millivolt per nanometer we apply, we get 1.4 Kelvin of a gap. So when you put bilayer graphene in a magnetic field, it develops Landau levels. And in the simplest model, the E equals 0 Landau level is 8-fold degenerate. So 2 comes from spin, 2 comes from the orbital degrees of freedom. The n equals 0 orbital is just like the ground state function of the wave function of the harmonic oscillator. And then n equals 1 orbital is composed of a majority of the first excited state wave function and a minority component that is the ground state wave function. There is another level of degeneracy that comes from the valley index, K and K prime, or plus and minus, or in this case, the +0 state is fully sitting on the top layer, and the -0 state is fully occupying the bottom layer. So that's also a layer difference. And it's almost the case for +1 and -1 with a little bit of the n equals 0 orbital wave function. So if I look at the +0 and -0 states, this degeneracy can be broken by applying a vertical displacement field, just like at zero magnetic field. And I can split this difference. And because these states are about a few angstroms apart, to a very good approximation, Coulomb interaction doesn't care which state it is occupying. So this valley isospin really looks like a spin degree of freedom. And I've shown you its G factor. So let me show you what the Landau level diagrams looks like. So I'm sitting in a fixed magnetic field and I'm dialing up this displacement field. So in a small d regime, this valley degeneracy is here, and we have a splitting between the n equals 1 and n equals 0 orbital because of exchange. Now, as I increase the valley splitting, at some point, the -0 and +1 cross one another. And after that, my states become valley polarized. So there are 4 of them here. And then I show the other 4. Turns out that Zeeman splitting is very much exchange enhanced in bilayer graphene. So at a reasonable magnetic field, this is the first thing that splits. So all of the 4 top levels are spin up and all of the whole levels are spin down. Now, if I keep increasing the valley splitting, I get a crossing at mu equals 0 from these 2 levels. And if I keep doing this, I get a second crossing from the -1 up and +0 down. And after that, I reach the large D limit where the order of the Landau levels no longer changes. So we put together this effective Landau level diagram in this work over here, combining our own measurements and a lot of the other measurements, some of which are listed here. And we provided fittings, empirical fittings for what the energy levels would be. So this plot here shows you these two crossing points at nu equals 0, this DH star and DL star. And you can see how it evolves with a magnetic field. So this effective diagram is pretty good in capturing a lot of measurements. Where it fails is when correlation is particularly strong. For example, for the nu equals 0, if you just look at the diagram, you might expect it to be all spin polarized. But it turned out, in fact, it is a canted anti-ferromagnetic state that has very interesting spin wave excitations. So I'm not going to talk about this today, but if you're interested, I'm doing a lecture at the summer school next month, also at Princeton, and I'll be focusing on that subject. So today I want to talk about this part of the diagram where you can see these 8 levels. Now, back in 2017, already both Corradin's group and Andrea Young's group have shown that these 4 states that ride on the n equals 1 orbital develop an even denominator fractional quantum states, as I show here. Now, you might wonder, as we go to smaller displacement field and enter the limit of what's on the left, does 5½ also develop into an even denominator fractional quantum states? Now, in this configuration, spin are all polarized. So this is a spinless liquid effectively, but we have the valley isospin here that plays the role of the spin. And since we can tune it with the electric field, we can go through 0 very easily. So this is an important, maybe allow us to address some of the important questions of the even denominator states. But in order to get here, we want to go to a small displacement field. And in previous measurements, this regime is largely not resolved, presumably because of disorder. So what I want to show you today is that after we made better samples with higher qualities, we can now see a lot more physics in this low displacement regime. And you will be seeing a lot of plots like this, where it's displacement on one x and filling factor on the other x. We're plotting the longitudinal resistance. Warm color is high resistance and cold color is low resistance. If you see a vertical line here, and that is a fractional quantum Hall state. So you see that here very clearly at 5½ we see signs of a fractional quantum Hall state. And you all see there's a lot going on in this range over here where the wave function rides on the n equals 0 orbital. So I'll be telling you about 2 things. First, I want to tell you about this new even denominator state at 5½ and I want to show you that it is spontaneously valley isospin polarized in the limit of vanishing valley Zeeman energy. And I want to show you how symmetry is broken around the even denominator states in bilayer graphene. And then I'll move on and show you the phase diagram of the fractional odd denominator fractional quantum Hall states around 3½ and how the valley isospin polarization changes as we change the displacement field, and how does that compare to other systems. So first of all, this is the map that I've just shown you again. Now, I marked the states where these fractional states ride on. If I take a line cut across here, you can see that both 3½ and 5½ ride on the +1 state. And indeed, if you look at the line trace, you see that 3½ is a even denominator states. This was seen before also. And the 5½ shows a very deep, nice minimum. We have checked that at least it survives down to 9 Tesla with a developing plateau in the Hall resistance. So it is a even denominator fractional quantum Hall state. Now, if you take a line cut across the +0 and the -0 states, we see the conventional fractional quantum Hall sequence that is the 2 flux composite fermions. So earlier this week, you heard that electrons and holes are symmetric around composite fermion Fermi-Cs. Now, let me compare the traces around the 3 even denominators in bilayer graphene, 3½ 5½ and 7½. And around 3½ we see the 11 helping daughter states of the Pfaffian, that's the 8/17 and 7/13. Around 5½ these two no longer fit, but rather the other daughter states of the anti-Pfaffian fit very nicely. And then around 7½ we go back to the daughter states of the Pfaffian. Now we also see a pretty strong 2/5 and 3/5 around 3½ and around 7½, and the asymmetry is consistent with the asymmetry of the Pfaffian. We also see weak but reproducible minima at 3/7 and 4/7 near 3½ So as you know, the 5ths and the 7ths are long suspected to be non-abelian states from earlier work of Reid and Rizai, and also from more recent work of my colleague Janandra Jain using a parton model. So we're looking into the nature of these fractional states. Now, let me briefly tell you a little bit about, and this is something that a lot of people already know, but I want to summarize it here. What is the state in gallium arsenide? So in gallium arsenide, around 5½ there are transport measurements that indicate the anti-Pfaffian. But if you heard talk from earlier this week, the thermal conductance measurement and noise measurement are more consistent with a particle called symmetric Pfaffian. So in our samples, we see that the 3 different states break the symmetry differently. And this Pfaffian around 3½ is also seen in Andreas capacitance measurement. So taking all together, this suggests to us that exactly how the symmetry is broken or whether it is broken depends on the specifics of the interactions. Now I want to focus on the 5½ state that happens at a low displacement field. Now we have taken temperature dependence measurement of the resistance at a different displacement field, and we have analyzed the data in terms of activated transport and pull out the gap of the 5½ state as a function of the displacement field for both negative D and positive D. And that's the data that's plotted here. So you can see that if I extrapolate the data from both sides back down to D equals 0, I end up with a finite gap of about 0.2 Kelvin. Now both that value and also the trend the data exhibits tells us that the state is spontaneously polarized at in the limit of 0 electrical valley Zeeman splitting. Now this is important because being a triplet in the spin or the isospin channel is a necessary condition of the Moore-Reid state. That question was asked of the gallium arsenide 2DEG for the spin sector. And I just thought I put a few here, some of the measurements from gallium arsenide. There have been a lot of transport measurements. And the bottom line is that transport is in a tilted magnetic field where you can tune the Zeeman splitting. It's kind of complicated because of the competing stripe state in the tilted field. There have also been NMR and more recently spin resolved tunneling measurements that generally are consistent with spin polarized states for the 5½ but you cannot go to 0 Zeeman splitting in these measurements because you need a magnetic field to generate the 5½ state. Now, by using the valley isospin and without changing anything else, we can go around this problem quite nicely. So now I want to move on to the second part and tell you a bit about the valley spin isospin polarization of odd denominator fractional quantum Hall states. So I show you the map again. So now we're gonna move to the states that occupy the +0 and the -0 orbitals around 1½ and around 3½ And you can see here from the line traces that in both regimes, we see nice fractional states that correspond to flux composite fermions. Now, if you look at this white box that I have boxed here, you see a lot of features inside this box. And let me zoom in into this area for you. So this is data around 3½ So you can see that there are places where the resistance becomes high, and that indicates a gap closing, for example, here and here for the 4/3. And you see a lot more as we move towards 3½ So these gap closing points, which I mark with the circles here, are valley polarization transitions of the composite fermions. Now I have mapped the fractions onto integer lambda levels of the composite fermions and put the integer level filling factor nu star on the top axis so that you can see what they correspond to. I see these are polarization transitions because of the following. Now let's take the example of the nu star equals 4 over here. So at the d equals 0, where there is no valley splitting, my plus levels and my minus levels are degenerate. So filling 4 states, meaning 2 plus and 2 minus. So this corresponds to a polarization of 0. Now, as I increase the valley splitting to more than 1 lambda level spacing, my filling becomes 3:1. This becomes a half polarized state. And as I keep increasing the valley splitting to 3 lambda level spacing, the state becomes fully valley isospin polarized. And on the negative side, I can do the same thing. So altogether, we have 5 ground states with different valley isospin polarizations separated by 4 transitions. And as you can see, there are indeed 4 transitions in our data. So using this free composite fermion model, we can explain all of the transitions that we see in our data. So here I'm showing a bit more data that was taken at 18 Tesla. These are taken at different magnetic fields. We're doing line cuts across a fraction. Whenever you see a resistance peak, that is a transition. And using data like this, we can pull out the valley Zeeman energy, the critical valley Zeeman energy that is needed to fully polarize a fractional quantum Hall state. And we can normalize that with the Coulomb energy scale and plot the alpha critical of these fractional states at different magnetic field. And that's what this plot is, alpha versus filling factor at different magnetic field. And first you can see that data from different magnetic fields collapse reasonably well. And this tells you that indeed EV scales with square root of B. You can also see this tent-like shape that's coming out of data, and that is expected by theory. So here I plot here the theory that is calculated for ideal 2-DAG with 0 thickness and no lambda level mixing. And the most notable discrepancy between our data and theory is that our numbers are a factor of 4 smaller than what theory says. So here's that comparison again, theory and our data. Now the red circles are data from gallium arsenide spin in a heterojunction. And as you increase the thickness of the 2-DAG, these data generally come down, and that's the shaded area. So I'm plotting also data from monolayer graphene and data from aluminum arsenide, but using valley transitions. And you can see that these two generally agree with theory pretty well. And it makes it curious, sort of, why does monolayer graphene agree with theory pretty well, and bilayer graphene is a factor of 4 smaller? And the answer most likely has to do with the effect of lambda level mixing in bilayer graphene. So I'm showing you this E=0 octet again. So I hope that I have convinced you that valley isospin is indeed a very nifty knob that we can use to control interactions in the quantum Hall regime. It's in fact a pretty unique knob for bilayer graphene because it's fully tunable by an electric field. And because we're doing that with a gate, we can pattern it, which means we can pattern the local ground states of fractional quantum Hall effects. And this tuning is independent of other parameters, Zeeman splitting or carrier density, or the interaction strengths, and so on and so forth. So from the example that I've shown you, you can see that it's really a very useful tool here. Now, the complication here in bilayer graphene is that, well, there are 8 lambda levels that are fairly closely spaced with one another for electron, 4 hole, and electrons and holes are not symmetric. So they don't cancel each other very well when you do the calculations. So it is a theoretical challenge, but I hope that the theorists can overcome this challenge to work on this beautiful system. So let me briefly summarize what I have shown you so far. So I've shown you that in higher quality samples, we see another even denominator states at 5½ and this state is spontaneously polarized in the valley isospin in the limit of vanishing Zeeman energy. And this validates a key property of the Moore-Reed state. I've shown you that the electron hole symmetry is broken near these even denominators with 3½ and 7½ going for the Pfaffian and the 5½ going for the anti-Pfaffian. We can control the ground state valley polarization of a lot of fractional quantum Hall states. And that behavior is in fact well described by a theoretical model that considers a spin-like index. So the valley isospin is really like a spin degree of freedom in our system. Where do we go from here? So we are in the regime where the valley Zeeman splitting is so small that we can probe some very interesting questions. For example, are there valley skyrmions at integers and fractions? And are there valley waves? Now, following these beautiful experiments that's done in other 2-DEC systems, and this is something that we want to look into. We also might be able to say something about what happens when you couple the fractional states with a superconductor, because we can control the valley polarization straightforwardly with gates. So there are proposals that would couple a superconductor with fractional states.
You're running out of time, so you should make an effort to wrap up.
Okay, thank you. I'm about done. So is it possible to use valley to construct these hybrid structures and probing these interaction in interesting systems? So I'd like to have the theorists help us think about that. So I want to acknowledge my people. The experiments are done by student Ke Huan and Dr. Hailong Fu, postdoc in my group. There's a collaborator in PKU, Professor Xiling, or my cross-fist at Penn State. HBN comes from Japan, and we thank our funding sources. And thank you for your attention, and I'll be happy to answer questions.
Well, June, thank you very much for the wonderful talk. I mean, the data at even denominators are really amazing. And we have a question by Onder Gul. It's a long question. Would you like to phrase it yourself? If you do, please unmute.
Yes, of course. Thanks for the talk. It was very nice. So there's a similar transition at high displacement between filling 0 and 1 for bilayer graphene. Have you also focused in that region?
Between 0 and 1.
So it's similar to like
Right. So between 0 and 1, we have focused in the low D regime. We haven't focused in the high D regime. Can people see my screen? Because I only have one screen.
Yes, we can.
I'm not sure what's showing, right? So in the low D regime, all the fractional states are spontaneously valley polarized. Now, I don't remember what happens in the high D regime.
So there's a very similar phase transition, just like the one you're focusing.
Yeah,
maybe
so,
if you have the data
right.
from, I think, yeah, you can see it there. One
yeah,
below.
so right. I don't think we didn't look carefully into the regime between 0 and 1. But since we saw everything else that Corey sees, I don't think it would be that different.
I see. So my question was mainly because you mentioned that disorder might be the reason why these states are not developed. So
Right.
there is no fundamental reason why these states would not develop, and in decreasing the disorder would resolve these features. Also
Well,
for
because,
the high displacement.
Right. So because the valley splitting, as I showed you before, right, 1 millivolt per nanometer gives you 1.4 Kelvin. So in order to resolve something of a few millivolt per nanometer, you really want your disorder to be lower than a few Kelvin. So if you have stronger disorder, you would simply smear it. You would not have a well-defined valley polarization in that case.
Thank you.
Mansour?
Yes, I have a couple of comments and a couple of questions. Well, first, nice talk. Thanks. The one comment is you mentioned that the spin polarization in 5.5 for gallium arsenide is not known and it needs a parallel field. That's actually not true. We reported some data, geometric resonance data, without any parallel field. You can see composite fermions that are fully polarized on the sides. I think Arhan has some data too from Raman spectroscopy. I don't remember if it involves parallel field. Second comment is you had in one of your slides that spin behave just like valley degree of freedom. That has been established in aluminum arsenide for years now. We measure the spin susceptibility, valley susceptibility, and that is clear. And so much of the phenomena that you discussed is seen in that system. Now, two questions. If you could show your slide 28, the 10th structure that you show. So you're looking at gallium arsenide heterojunction, and then your data is at the lower, right, bilayer graphene.
Right.
Yes. So in gallium arsenide, if you have a layer thickness, so again, this is well established. I could refer you. Then that whole 10th comes down for spin.
Correct.
And
that's
right.
That's what that's because I don't want to crowd this plot.
Right.
That's
right.
what this shaded area represents.
Right. So I don't know if it explains it because in graphene, I don't know how to define layer thickness there, but something to keep
very small.
Yeah, exactly.
Very small. So, right.
So that's right. And then another question I had was you showed a trace that shows 3/2 fraction quantum Hall, and then on the sides there are fifth states. I think it's one of the cuts.
This one?
Yeah, for example, right. The one on the left.
Right.
The trace. So yeah, the trace on the left, which is shows 3/5 and 4/7 and so on. Right. So as you said, in the n equal to 1 lambda level in gallium arsenide, when you see 5/2, the fifth states are extremely weak. You have to go to a couple of millikelvin to see them. In wide quantum wells, where we see a 3/2 state or 1/2, and in fact the other fractions near it, it looks more like this. I could show you traces in these wide quantum wells, bilayer like charge distribution. And I wonder if this 3/2 you see here is not a 2-component state. How are you sure that this is a Pfaffian state?
So there are several pieces of evidence, right? So first of all, you got the daughter states of the Fafian. Second of all, so the 3/2 is spontaneously valley polarized and spin polarized by virtue of being in a large magnetic field and in a large displacement field. So you can see that where they sit on this energy diagram. So these are, so it's spinless and it's valleyless. There is no a two-component state, for example, 331 would be unpolarized in the spin or the isospin sector, right? So here we have spin polarization and valley polarization into the daughter states of the Fafian. So I don't see how it can be.
I don't think I agree. If you go back again to that slide that I was asking, because that shows it more clearly. You know, in these wide quantum wells again, you see same sequence. You know, there's 5/3, you know, 3/5 on the other side. These are, you could consider them dollar states of the regular, you know, 4/3. The next one should be 2/5, 3/7. That's the usual sequence. So it's not necessarily the daughter states of the Fafian state. And
so
some of these states.
Master, let me just, sorry to interrupt a little bit. When I say the daughter states, I mean the 8/17s and the 7/13s.
Oh, you don't mean the sequence?
I don't mean the 5th and right.
The states that start from the.
I mean the 8/17s and 7/13s.
I see. Okay, I see. Okay.
Right. Sorry for interrupting, but I halfway somewhere I figured that you misunderstood what I meant. And thanks very much for the comment on you know, the valley degree of freedom. Of course, valley degree of freedom is also a spin-like degree of freedom in aluminum arsenide, and you can tune that with strain. Right? I don't mean to say that bileographene is the only thing that has a valley degree of freedom. What I wanted to say is that it's unique in bileographene because we can tune it with the electric field. And it does show behavior that's similar to what the valley does in aluminum arsenide, as you can see from the comparison between our data and your data.
Yes, thanks.
Okay, thank you, Mansour. And so I don't see more questions. So we thank Professor Junju for her excellent talk and the thorough description of her recent work. And before calling for the next paper, which is the last paper of this session and of this conference or workshop, I would like to express, I don't know exactly how to say, gratitude or highlight the fact that the Mansour has done an outstanding work in organizing this work on very short notice. And it seems obvious to me that the Princeton team that he put together has also done outstanding work. And we are very grateful for this contribution to the community and to the field of quantum Hall effects. Perhaps out of the participants in this workshop, there is going to be an organizer of the next EPQHS. There's a lot of stuff we have going on, so maybe it's likely we are going to see an EPQHS9. So at this point, I call for the next talk by Professor Barkesley of University of Maryland. Professor Barkesley will talk about new topologicals invariant. Thank you. Please go ahead.
Thank you, Aaron, for the introduction. And thanks, Mansour, for inviting me and for organizing this. I'm very surprised to see a single organizer for a conference like this. So thank you very much. I'm going to be talking about work that I've done over the last year with my student, Naren, which is summarized in these two papers. posted over the last year. So, you know, some of the most striking properties of fractional quantum Hall states are the fact that they have topological invariance, right? And topological invariance, if you think about what it is, what we mean is it's a physical property of your system which is robust to all perturbations that keep your state in the same phase of matter. So these are fractional quantum Hall effect has all these famous topological invariants doing fractional quantized Hall conductivity, fractional electric charge of the quasiparticles, fractional statistics of the quasiparticles, quantized thermal Hall conductance, and then there's a constraint that the filling fraction is given by the Hall conductivity. And remarkably, all of these topological invariants have been measured experimentally due to, you know, brilliant work over spanning decades involving tight collaboration between theorists and experimentalists. It's really quite amazing when you think about it. So now what I want to do is let's think about these topological invariants and let's try to ask, you know, what else is there? Did we miss anything? And is there more? Are there more things potentially that we could measure that give topological invariance? So when we think about topological invariance, I think the first important thing to realize is that some of these invariants require symmetry to define. Like the fractional electric charge and the fractional quantized Hall conductivity, the only reason they have any meaning at all is because we have U1 charge conservation symmetry. So we can ask about the U1 charge, we can turn on electric fields and measure finite conductivities and things like that. So I would refer to these as symmetry protected topological invariants. In this case, they require this U1 charge conservation. There are other invariants that do not require any symmetry whatsoever. These we would think of as intrinsic topological invariants. So these would involve the fractional statistics of the anyons and their fusion rules if you have like a non-abelian state, for example. So some of these intrinsic topological invariants, we have a pretty good theory for what they all are essentially. And for example, there's some finite set of topologically distinct quasiparticles, and we can look at basically mutual braiding, and we can look at exchange statistics, and these give us invariance. And then there's the chiral central charge. So even though it's often said that fractional quantum Hall phases are, you know, topologically ordered states or topological phases, it's actually good to emphasize that they are paradigmatic examples of symmetry-enriched topological phases because the symmetry is interacting with the topological properties in this highly non-trivial way. So now this raises the question, so suppose that you're given some fractional quantum Hall problem and you know what the complete symmetry group of your system is. Then you'd like to ask, what is the full set of topological invariants, both symmetry protected ones and the intrinsic ones? And what are their physical properties? What signatures do they have in numerical simulations and in experiments? So we have a theory now, for the most part, to answer these questions. For intrinsic topological invariants, we have a mathematical framework, which is called unitary modular tensor category theory. And sometimes to not scare away most physicists, it's referred to as the algebraic theory of anyons. And the basic point is it's just a mathematical theory that captures the fusion and braiding properties of anyons. And it's been kind of developed over the last 30 years or so. Now, if you're asking about symmetry protected topological invariance, so how the symmetry interacts with the topological order itself, over the last few years, we've also developed a theory that goes by the name of G-crossed braided tensor categories. And there, the idea is basically to try to think about the properties of braiding and fusion of anyons together with the symmetry defects or fluxes of the symmetry group, and try to develop a kind of comprehensive theory that would work for any symmetry group. So some kinds of symmetry groups we would be interested in the fractional quantum Hall problem, particularly single component fractional quantum Hall systems. You know, of course, there's charge conservation, which is the most relevant one if you have disorder in your system. But it's also interesting to think about continuous magnetic translation symmetry and spatial rotation symmetry. So this is relevant for clean fractional quantum Hall systems. And given that fractional quantum Hall materials are so exquisitely clean, it is quite possible that we would even be able to experimentally observe certain properties of the system that rely on having continuous magnetic translation and rotation symmetry. In this case, the symmetry group would be the Euclidean group, which includes translations and spatial rotations. And then there's the U charge conservation. And this funny symbol is just there to emphasize the fact that translation symmetries don't commute. So technically you have a more complicated group where the U1 is intertwined with the translations. Now we can also consider fractional quantum Hall states on the lattice. And in particular, sometimes we have very strong lattice effects, like in fractional Chern insulators, which have also been seen experimentally now in Andrea Young's group. And in this case, we would be interested in discrete magnetic translations and M-fold point group rotations. Now, once we start thinking about multi-component fractional quantum Hall systems, then the symmetry groups are even more complicated. The U1 gets replaced by UM, and then we just take some subgroup of UM, which is intertwined with the translation and rotation symmetries as well. So these are the kinds of symmetries that we would be interested in asking, what kinds of topological invariants do we have? Now there's a kind of technical point, which is the theoretical framework that we use to develop this theory is basically that of topological quantum field theory, where you have an internal symmetry group G. So you might ask, does this theory apply for spatial symmetries as well? And there's no mathematical proof, but it's kind of an assumption that the spatial symmetries can be treated on the same footing as on-site symmetries. And this follows some general expectation from quantum field theory of many body systems and a lot of experience that we have over decades of how quantum field theory emerges from many body systems. And there's also a lot of evidence from it in some class of topological phases that have been studied over the past few years. And it also matches all other known results that are obtained in other ways previously. So our strategy is going to be, we're going to follow this theoretical framework with this treating spatial symmetries the same way as internal symmetries. And then we're going to develop a physical interpretation for what we get. And then it's ongoing work to look at these predictions, try to come up with microscopic models where these are realized, and then study them via calculations on microscopic models as well. But this is really future work. At the moment, I don't really have that much microscopic models. I have a kind of theory that predicts universal properties like these, that I'll tell you about. So before I kind of tell you some general results, let me give you one more example that is already known from almost 30 years ago. So if you take continuum fractional quantum Hall states in the clean limit, where you have continuous rotational and magnetic translation symmetry, then not only can you define fractional electric charge of the anyons, you can also define a fractional orbital angular momentum. So you can understand this in a Chern-Simons field theory, like a Chern-Simons Lagrangian, and this was done by Wen and Z, where you just write down the Chern-Simons term that describes your 1/Q Laughlin state, for example. You include the coupling to a background U1 gauge field, but now because you have continuous rotational and magnetic translation symmetry, you can actually couple your theory to continuum geometry of the system. So you can introduce a new U1 gauge field, omega, and omega technically, it's like a gauge field for spatial rotations. So the curl of this gauge field gives you the spatial curvature of the system, just like the curl of the background vector potential gives you the magnetic flux. So this omega is like a spatial rotation gauge field, and that can also couple to the theory. So there's this new parameter that enters the theory, which is sometimes called the spin vector. And the essential physical consequence of the spin vector is that if you were to take a quasi-particle, which has charge k over q, around some region which has a curvature angle of omega. This gives an Aharonov-Bohm phase of e to the I omega times the total spin of the quasi-particle. And now this total spin of the quasi-particle gets a contribution from this spin vector over here. So you can think of one piece here as like a fractional orbital angular momentum, and the other piece is like some intrinsic topological angular momentum. And there's a nice paper by Andrei Gromov a few years ago where he does this calculation actually for this theory, and he shows how that comes out. So in general, when we want to think about symmetry protected topological invariance, there's two classes of invariance to think about. One is the fractional quantum numbers of the quasi-particles. So this we refer to as symmetry fractionalization. So this is just like what the examples that I've mentioned so far. You can have fractional electric charge, fractional orbital angular momentum, and then on the lattice you have even more, which I'll describe. And the way to think about these fractional quantum numbers is that it's very much inspired by basically what Laughlin did originally. What you do is you insert some quantum of flux. So in the case of U1 symmetry, we adiabatically insert 2 pi flux. But in general, there's always some notion of a quantum of flux, which generalizes the 2 pi flux in the U1 case. And that insertion of a quantum of flux will induce some anion in the system. In the fractional quantum Hall case, that's the Laughlin quasi-particle. And then you can define a Aharonov-Bohm phase for any anion by braiding that anion around the anion which is induced by that quantum of flux. So in the case of U1, again, you have some anion V which is induced. Then you can define the fractional charge of every other anion by the mutual braiding between that anion and the induced anion V, where M is this mutual braiding phase. Now, this basic idea is quite general, and in fact, you can develop a mathematical theory where you classify all possible types of symmetry fractionalization, and it turns out there's a classification using group cohomology to do this, and it applies to both abelian and non-abelian fractional quantum Hall states. So we can apply it in complete generality. The other main class of invariants are fractionally quantized responses, like the Hall conductivity. And the basic point about these fractionally quantized responses is that they are basically defined by attaching some G charge to some G flux. Okay. Now, how do you define G charge? Well, one way to define charge is by the phase that you get upon braiding with a flux. Okay. So what this means actually is that if you know how to braid, if you keep track of phases that you get by braiding G fluxes around each other, you can figure out what the G charge is that is attached to a G flux. This is the general idea, which is very familiar for Hall conductivity. Now, to fully understand these quantized responses, we also have to understand integer responses, and we have a classification for that as well in terms of group cohomology, which is applicable for bosonic systems. And for fermionic systems, the analogous thing is much more complicated, and it's still to some extent under development actually. And then the fractional part of the response is fully determined by the fractional quantum numbers and the fractional statistics of the anyons itself. So once you know the fractional quantum numbers of the anyons and you know their fractional statistics, you can immediately determine the fractional part of these quantized responses. So, we're going to be interested in like spatial symmetries in this talk. So what is the physical meaning of charges and fluxes? Well, U1 symmetry, we know it's electric charge and magnetic flux. If you have some continuum spatial rotational symmetry, the charge is orbital angular momentum. The flux is geometric curvature. If you have continuous translation symmetry, the charge is linear momentum. The flux is what's called geometric torsion. It's basically a geometric continuum version of a lattice dislocation. If you have point group rotational symmetry, then the flux is a lattice disclination. The charge is a discrete angular momentum, which is only well defined modulo M, because you can't do rotations with angles smaller than 2 pi over m. If you have discrete translation symmetry, the charge is linear momentum. Now it's defined modulo 2 pi over the lattice spacing. And if you have, and the flux is a lattice dislocation, okay? So ultimately, we're going to be developing a theory where you attach charges of one symmetry to fluxes of another symmetry, and we figure out what the quantized way to do these is. So let's go back to symmetry fractionalization in the continuous case. So here, remember, now, here there's two things. It turns out, if you want to do a comprehensive classification, it turns out we didn't miss anything 30 years ago. You have the flux, you have the anion induced by 2 pi flux insertion, that's V. Then the fractional charge, as I said, is the braiding of V with A. The fractional orbital angular momentum is defined in almost the same way. You insert 2 pi flux of curvature, basically. That induces another abelian anion, which is the analog of the Laughlin quasiparticle, but for curvature. This abelian anion is sometimes called the spin vector, but this idea is applicable in general for both abelian and non-abelian fractional quantum Hall states. When Wen and Z introduced the spin vector, they were only focused on abelian fractional quantum Hall states. And now, once you know this S, you can define the fractional orbital angular momentum by braiding any anion with the anion induced by that 2 pi the insertion of 2 pi curvature flux. So in the continuum, now we go to fractionally quantized responses for continuum fractional quantum Hall states. Here again, now we have the Hall conductivity. We have the shift. The shift is physically what it does is that it attaches charge to geometric curvature, and it attaches angular momentum to magnetic flux. And one consequence of attaching charge to geometric curvature is that if you look at the number of electrons on some compact space with an Euler characteristic chi, there's a relation between the charge, the number of the number of particles, and the number of flux quanta, which is the Hall conductivity, but then there's an offset over here, which defines the shift. Okay, so people who work with numerics and fractional quantum Hall systems on the sphere are very familiar with this. There, the Euler characteristic is 2, and so you have this offset over here. And then we have the analog of Hall conductivity, but for the continuum rotational symmetry, the SOT rotational symmetry. So just like the Hall conductivity attaches charge to flux, this attaches angular momentum to geometric curvature. And all of this can be packaged into a nice response theory, which has been studied over the last, starting with Wen and Z, but even up to like 5 or 6 years ago, these things were under intense study. So you have the terms that are encapsulated in this way. So now let's go to discrete magnetic translation rotation symmetry and ask if anything new comes up that would be interesting. So the fractional quantum numbers of the anyons, it turns out we still had what we have before, except now the angular momentum is only defined mod m, and it can only be non-trivial if there's some commensuration between m, the order of the point group rotation symmetry, and the properties of the fusion of the anyons. So I'll get to this soon. In addition to these two, though, there's 2 additional fractional quantum numbers as well. It turns out there's a fractional linear momentum, which is only non-trivial with 2, 3, and 4-fold rotational symmetry. And then, or it can only be non-trivial for these symmetries. And then there's another quantum number, which is about the fractionalization of the translation algebra. So in this talk, so these two have no analog in the continuum. And in this talk, I don't know how much time I'll have, but I hope to discuss these two and leave the last one out. Now, when we look at the fractionally quantized responses, remember in the continuum, we only had 3. It turns out now we have 9 fractionally quantized responses. There's the Hall conductivity. There's a discrete version of the shift, which binds fractional charge to disclinations, lattice disclinations, and it also binds angular momentum to magnetic flux. There's the angular momentum of the disclination. Then there's,
Sam, you have 11 minutes.
okay, thank you. Now, these three are, there are analogs in the continuum, but now we have responses that have no analog in the continuum as well. There's a fourth one, which is a fractional quantized charge polarization. What this does is that it binds fractional charge to lattice dislocations, and then it also binds linear momentum to magnetic flux. There's the rotational analog of this, which is fractionally quantized angular momentum polarization, which binds angular momentum to lattice dislocations. Then there's filling fraction, which is the charge per unit cell. Maybe people don't usually think of the filling fraction as a response, but you can think about it as the response of the charge to increasing the area of the system. So in that sense, it's a response. But in reality, it actually plays the role of a constraint, because the charge per unit cell is something you fix microscopically. So this particular one is more like a constraint. There's a rotational analog of charge filling fraction, which is the angular momentum per unit cell. There's the linear momentum per unit cell. And finally, there is what we call a fractional quantized torsional response, which assigns linear momentum to a lattice dislocation. Okay, so there are all these different quantized responses that come out of the theory that we can think about. So in this talk, I obviously don't have time to get into all of this. I'm going to hope to explain something about the discrete shift and this fractional quantized charge polarization. Okay, but before I talk about the responses, let's go and talk about these two fractional quantum numbers first. So this is our symmetry group, is the discrete translations, rotations, and charge conservation. So here we have this fractional angular momentum. So how do we think about this? Well, we still have a spin vector, like in the case of continuous rotational symmetry, except now this spin vector is actually only interesting up to some equivalence relation. So really, there's only an equivalence class of abelian anyons, where the equivalence is defined here, which specifies the fractionalization. So we can think of this as a discrete version of the spin vector, which was introduced 30 years ago. So the idea here is that consider M separated ZM fluxes. So if you're on a square lattice, for example, this would mean consider 4 well-separated pi/2 disclinations. Okay? So 4 pi/2 disclinations fuse to a 2 pi disclination, which has no rotation angle around it. So we can think of this composite of M ZM fluxes as being a quantum of ZM flux, similarly to how 2 pi magnetic flux is a quantum of magnetic flux. This induces an abelian anion, just like 2 pi flux induces an abelian anion, the Laughlin quasiparticle. And this abelian anion is what we refer to as S. Now, S should be viewed as trivial if we can fully account for it by just fusing each individual one of these disclinations with some anion A, which can just be done by adjusting some local energetics at the disclination. So the important thing here is that this is the fact that M ZM fluxes are fusing to this anion S cannot be accounted for by each individual ZM flux is bound to some anion. Okay, so this statement is why we have this equivalence relation. Because if S is just some M multiples of some other anion, you could think about it as coming from fusing the elementary disclinations with this anion A. Now, transporting an anion A around M disclinations gives us a 2 pi rotation of the anion, which tells us what the angular momentum of the anion is, but it's equivalent to braiding our anion around this S, this spin vector. So that defines an orbital angular momentum by braiding A with S. So let's do a quick example. Let's take the bosonic 1/2 Laughlin topological order. This phase has two types of quasiparticles, the trivial and the non-trivial one. And then this is the statistics of that non-trivial quasiparticle. When we have 2, 4, and 6-fold rotational symmetry, we have two choices for S, which means that the fractional angular momentum can be either -1 or 1 here. So the total spin is going to be this extra orbital angular momentum piece plus this intrinsic spin of the anion. So you have these two different choices. But interestingly, if you had 3-fold rotation symmetry, there is no non-trivial notion of rotation symmetry fractionalization. You have to have a commensuration between M and the order of the anion here, which in this case is 2. Now, we also have fractional linear momentum. And this case is kind of similar, but it's actually much more complicated in some ways. Here, this is characterized by some equivalence class of a pair of anions. So we can call this the discrete torsion vector. And the equivalence relation is given here, where this U is a 2x2 matrix, which is the generator of this 2π/m rotational symmetry in the lattice basis. It turns out that this discrete torsion vector, because of this equivalence relation, can only be non-trivial when you have 2, 3, and 4-fold rotational symmetry. In this case, the quantum of translation flux is a lattice dislocation, which has a Burger's vector that takes this form, where lambda is an integer vector. And this quantum of translation flux induces an anion, which is T dotted into this vector lambda, which is given by this guy. So now this, just like in the previous case, this can define a fractional linear momentum by braiding the anion A around this quantum of translation flux. So we can define a fractional linear momentum in this way. So I have an example here for the 1/2 Laughlin phase, but in the interest of time, I'll skip it because I want to get to these two fractionally quantized responses. So one is the fractionally quantized charge polarization. Here, there's some number P, there's a vector PC, where what it does is that it attaches a U1 charge, PC dot B, to a dislocation which has Burger's vector B. Now, it's attaching charge to dislocations. So there's also a dual response where you attach momentum to 2π magnetic flux. So it also attaches a linear momentum PC to a 2π instanton, i.e. a 2π flux smeared over a large region. And then in addition, this induces a charge per unit length along the boundary of the system, which is one reason why we call this a charge polarization. So the system on a space with boundary will have a fractional charge polarization. Okay, so there's a formula for this, but it doesn't really matter for this talk. Let me give you an example. Let's again go back to the 1/2 Laughlin state with two quasiparticles, and where this non-trivial quasiparticle has charge 1/2. Okay, and let's do this on a square lattice. I didn't really go through this example, but in this case, we have two distinct choices of this discrete torsion vector, which it can be either 1, 1 or E1. And let's consider the non-trivial choice for this invariant. So what this means is that a dislocation with this Burger's vector, a Burger's vector of this form, induces this anion. So let's unpack that. That means if I pick lambda1 equals lambda2, for example, B is just going to be 2 times y hat. And if I pick lambda1 is 1 and lambda2 is -1, that's going to be 2 times x hat. So what this means is a lattice dislocation with these two Burger's vectors, either this one or this one, induces the Laughlin quasiparticle, which carries charge 1/2. But this is actually twice an elementary dislocation. That means an elementary dislocation actually carries is like half of this anion. So therefore it carries a charge of 1/4. So this means that elementary dislocations in such a phase would actually carry charge 1/4, even though the minimal charge of the anion is 1/2. And in fact, this 1/4 is only even defined mod 1/2 because I can always bind an anion to a lattice dislocation by adjusting the local energetics of the problem. But I can never bind 1/4 charge by adjusting the local energetics of the problem. So this is an example where the dislocation kind of fractionalizes the anion into 2, and a 1/4 charge is on an elementary dislocation. If you
Marshall, you really have 5 minutes.
Oh, okay.
Those 5 minutes were meant for discussion. So
Okay, so I'll just end. So there's a similar analysis for the shift, which will tell us that a single 2 pi over m disclination can carry the charge of our spin vector divided by m. So again, this is a fraction of an anion attached to an elementary disclination. So let me just mention the 1/2 Laughlin state example again. If we go back to the square lattice, if we pick the non-trivial choice of the spin vector, it means the pi over 2 disclination can carry charge of 1/8. And if we did the 1/3 Laughlin state instead, we can go to a honeycomb lattice, and if we pick this non-trivial spin vector, the elementary disclination charge will be 1/9. And if we look at the dislocations, the elementary dislocation charge can also be 1/9. Whereas if you look at the triangular lattice, it becomes a 1/18 for the disclination charge, but there's no non-trivial choice for the dislocation charge because, well, it's a bit complicated. Why not, actually? And then if you look at square and rectangular lattices for the 1/3 Laughlin state, it turns out there are no non-trivial choices for this spin or discrete torsion vector. So we have no particularly interesting fractionalization of the anion in these cases. Okay, so let me just end there with, actually, yeah, let me just end there. And as my summary, I'm just gonna put up this table of the list of fractional quantum numbers and the list of fractionally quantized responses that you can stare at during the questions.
okay. Well, thank you very much. I have to admit that I recently sent a note on angular momentum or spin, and I know that my point of view was very, very naive. You explained a lot of properties which I was not really familiar with about angular momentum. So thank you very much for a talk which overall has been exciting. So we have a couple of questions at this point. There is Song Yang Pu who asks, how does Hall viscosity fit into this theory?
Well, okay, that's an excellent question. Hall viscosity is, physically, it's different in the sense that it's a viscosity, but when you have rotational symmetry, its value is actually set by the shift in the continuum. So it's not a new invariant, but it's a new manifestation of, where's my, sorry. Yeah, so we have this response theory. So the coefficient of this omega dA term is what sets the Hall viscosity. So the Hall viscosity is not a new invariant. It's just, it's a new physical manifestation of this particular topological invariant.
Okay, there is a question by Duncan, but it would be better he formulates the question himself.
Yeah, okay. So yeah, continuous rotational symmetry is certainly a feature of the Laughlin wave function, but it's actually not a fundamental part of the fractional Hall effect because it's not a protective symmetry and you deform it away. So for example, the Hall viscosity is really related to the electroquadrupole moment, and it happens to coincide with the shift for rotational symmetries. So shouldn't really the analysis you're showing, you should apply it only to systems where the extra symmetry is a protective symmetry.
Yes, yeah,
as
exactly.
opposed to an accidental symmetry. From that, if you want, rotational symmetry is accidental from the point of view of fractional quantum Hall effect.
Well,
because it's not a fundamental symmetry.
I don't know what your definition of fundamental or not is. Depending on the microscopic setup of the system, rotational symmetry could be an excellent approximation.
Yeah, but it's not a protective symmetry. You tilt the magnetic field, it's gone. Therefore, I mean, unless there's some stability of the thing, for example, the whole viscosity is no longer quantized. It's accidentally quantized because it's a spin times an electron density in the.
Well, but anytime you have some condensed matter system, almost many symmetries are accidental, right? Like point group symmetries are in some sense accidental. If you kind of strain your system in some way, you can get rid of your crystalline symmetries. So I agree with that. What I said is only applicable to a system which has these symmetries as exact or highly accurate symmetries of the microscopic system. But depending on the physical situation, it may or may not be reasonable to think about those symmetries.
No, but I think you should apply it to states where the state only exists when you have that symmetry, right? And the sense is not a Laughlin state which doesn't require rotational symmetry, but some other kind of state, possibly some way on a lattice where there's some, mixture of plaquettes of different amounts of quantum Hall or something. You need something where the actual symmetry is, where the state doesn't exist without that symmetry.
But in this case, without rotational symmetry, I would have one kind of Laughlin state. Whereas if I impose rotational symmetry, I could have multiple distinct phases which have the same Hall conductivity, same fractional statistics, but they're still distinct phases because there's this topological invariant that distinguishes them.
Well, if you want to classify accidental symmetries, sure.
I mean, I wouldn't call this accidental, but
if it's not fundamental, it's got to be accidental, right?
Well, then point groups, then crystalline symmetries are all accidental symmetries. They're not. None of them are fundamental. The only fundamental symmetries are the ones that come from standard model.
I would disagree, but anyway, let's move on.
Even then, you have quantum gravity, which has no global symmetry. So
there's a question by RM who we don't know his full name, and then you have this symbol XJ in many slides. What does it mean? How can I measure it in the lab?
XJ?
That's what it says. Can you, RM, can you clarify?
No, RM is in the attendees, so he cannot speak, but it's absolute value of X, I think, no? X,
That's what I mean, so it's a vertical bar missing.
yeah.
Okay.
I don't know which XJ. I mean, there's a.
No, it's not XJ, it's modulus, absolute value of X.
Ah.
I'm sorry, I don't know what
Yeah, I don't know what it means.
I think I know what it means. Here in this slide, wait. Here you have Z2 and then Zm. That symbol he's asking.
Oh, okay, yeah. This thing is meant to denote that this group is not a direct product between U1 and the other factor. It's actually a central extension of this space group by U1. So if I put a times here, you would think it's a direct product. I could put a times with a subscript that to remind you that translations don't commute, but they only commute up to this U1. But I chose to use this symbol to emphasize the fact that you have this non-trivial tying in between the charge conservation and the translations.
Okay, Mansour, would you like to say a few words?
Oh, yeah, I could just again thank everyone, the advisory committee who helped me, find suitable speakers and find and invite them. So that has been wonderful. Thanks to all the speakers, all the chairmen. Thanks to Klaus for being a special guest. So I just wanted to tell you there have been around 400 who signed up for the conference, for the workshop, and about 100 on the average showed up. So that's pretty good, I think. But to me, most important is the fact that we had many questions and good discussion. So thank you all again. It will be The recordings will be posted soon, so you can watch them and enjoy them. Great. See you guys at the next workshop or in person. Bye.
Thank you.
Mansoor, thank you very much.
You're very welcome. You're
Thank
very
you.
welcome. Thank you.
Hey, thank you, Mansoor.
Thanks. Thanks, Joe.
Thank you, Mansoor.
Okay, goodbye to all.
You're very welcome. Thank you.